So last time, trying to look, where did we leave off? Oh, right here. Oh, didn't I give this to you as homework?
No.
Oh, I should have. Oh, you already did this whole thing as homework.
Yeah.
Okay. So add a non-op node. So we wrote the easy version, the easier step. So if we're adding a non-op, we're going to try to add it to the left first, right? So if the left is null, we'll go ahead and add it. Otherwise, if the right is null, we'll add it to the right, knowing it's probably going to temporarily be added to the right unless this is a very simple expression. Else, we need to ask our right node to add this non-op. So we need to go into nodes, and we need to teach them how to add a non-op node. Okay, so if we are asking a node to add a non-op node, that means what? That means that I am not null, correct? Because we're only calling this guy under the premise that the left child was not available and the right child was not available. So if we know we have a right child, we'll ask that right child to try to add this node. So if I get into this code right here, if I'm that right child and somebody's asked me to add the non-op node, I know that I exist. Therefore, I'm not even going to try to add it here. I'm going to try to add it to my left node, and if I can't add it there, I'm going to add it to, I'm basically going to do very similar code, right? So I'm going to say if this dot left child is equal to null, if that's a true statement, I'll say this dot left child is equal to n. Else if this dot right child is equal to null, this dot right child is equal to n. Else this dot right child dot add non-op node n. That make sense? All right, question about that. So this should allow a non-op node to get into the tree somehow. Okay. Let's go back to our source reader, where we're reading in our tokens. So here's our token stream. We get our token stream, we build a brand new token out of whatever the current token is. If we don't have a syntax tree currently, we'll build one with that token. Otherwise, if the token is an operator and the tree already exists, we'll build a brand new tree with that token. Then, if the syntax tree's root is an op, we'll add temp tree to the right branch of that syntax tree. How do we do that? How does that part happen, the way we've written our syntax tree? If we go into our tree and we add an op node, so we know the tree exists currently, right? And we add an op node. If the root is already an operator, we go to the, we try to add this to the right, correct? But if the root is not already an operator, and that is the root of the tree is, well, the tree exists, so the root of the tree must be a non-operator, then what do? We set the left child of the new node to root, and we set this dot root equal to this guy. So we no longer are building that secondary tree. We're letting the tree handle who the new root becomes. So if we get inside of here, we don't even need this structure. If temp is op and we have a syntax tree, then this dot the syntax tree dot add op node temp. Else, this dot the syntax tree dot add non-op node temp. That should put the guy into the tree, flying through the filters that we've already put in. So regardless of our first node, whether that's an operator or a non-operator, if we don't have a tree, build a tree. Otherwise, if it's an op, add an op to the tree, and it will do whatever is necessary to add that op to the tree. Either replace the root node or send it to the right side. Else, if it's a non-op, we'll add a non-op to the tree. Make sense? Okay. So this should work. Let me quickly go into my what's the name of my source code?
My first program.simon.
Okay.
It's right there.
So for right now, I'm going to take out those second two lines. We'll talk about that while we're doing that. So we're just going to parse a single line right now. Okay, because we're going to end up talking about why languages work the way they work. Last thing we want to do is we want to teach our tree how to display itself. Public void display. So this is our syntax tree. What does it mean for a tree to display itself? Well, it should probably show the root node. And then the root node would display its left and right. And each of those nodes would display their left and right. Does that make sense? So probably the quickest way to write a display method is to add a function to node called display. And display does the system.out.print this dot token. And I guess for right now, let's just do a println. Then we'll do a system.out.println. Well, actually, sorry. We'll do a system.out.print left. If this dot left child is equal to null, system.out.print null, else this dot left child dot display. Similarly, for right, we'll display the word right. If this dot left child, or this dot right child, is equal to null, print out null. Otherwise, we'll tell the right child to display themselves. So just by calling display on the root node, all the nodes underneath should go and display themselves in some sort of weird way that we should be able to hopefully visualize enough to know if we got this correct. All right, so inside syntax tree, the display method just says this dot root dot display. And that guy gets the ball rolling. And what does that mean? He prints out his token. Then he prints out the word left. Here, I'll put a little colon after these lefts. Put a little colon into it.
Super gross.
It's quad luge, dude. Why you gotta make it weird?
Quad luge.
All right.
Because someone started doing that.
So we'll print out the word left. If we don't have a left child, we'll just print out, we'll do a println null, so it'll kick it down a line. If we do have a left child, then we'll ask that child to print itself. Okay? Otherwise, well, as well, we'll print out right. If we don't have a right node, print out null. Otherwise, we'll ask our right child to print itself. And keep in mind that our right child is also a null, or a node, so he's going to go through all this crap too. All right, so back in our source reader, at the end of this for loop, we should have a syntax tree, is the theory. And what are we going to do? We're going to say this dot, the syntax tree dot, display. And hopefully display that guy. Okay, so we already have our lexical analyzer. What does our lexical analyzer do currently? It goes through and it fills up our token stream. Then we're going to call our syntax analyzer. So step 2 of the compiler is source.syntax analyzer. And this guy should go through all of our tokens right here, build a syntax tree out of them, and then hopefully display the syntax tree in some sort of way that makes some sort of sense. Okay, so let's try to run this and see how bad it is. All right, so we have the equal sign. To the left of that is ID1. To the left of ID1 is null. That's good. To the right of the equal sign is, oh no, I'm sorry, to the right of ID1 is null also. To the right of the equal sign is the plus. To the left of that is ID2. To the left of ID2 is null. To the right of ID2 is null. To the right of the plus sign is times. To the left of the plus sign is, to the multiplication sign is null. To the right is also null. Okay, so let's look at our, I actually think we did fairly well, but I think we're missing some. Okay, so we got everything up to this last guy. So something got stuck. Actually, it looks like we didn't get any of our non-operators. Isn't that what it looks like? All of our operators got placed correctly, I believe, didn't it? Oh yeah.
Can you scroll down?
No, this is all it has. Yeah, ID1, ID2. Let's just for let me just quickly let's go into node. I'm going to go into the constructor for our node, and I'll just do a quick system.out.println creating node token. And hopefully we'll see at least that all the tokens are getting read in, just for our own sanity. Okay, so creating ID1, ID2, ID3, and 60. Okay, so we definitely created those nodes. All right, so now we got to figure out why the nodes didn't, why we kind of stopped after ID2. That's right, we were quad luging. It's luge.
How's it become a sport? Like, hey, I bet if this next one friends on a sled race down a hill faster than you can. I think that's how. I think most of that stuff starts when you're at a bar drinking.
If it's almost a sport, it's on ESPN 8, the Ocho.
Sad thing is, that's like I think they're at 7.
Who wouldn't watch that station? Does everybody know what movie that reference is from?
Yes.
Dodgeball. If it just shows some people just hitting each other with bamboo sticks, it's almost a sport. It's on ESPN 8.
bold move counts.
Have you ever seen ballet skiing?
Ballet skiing?
It used to be an Olympic sport.
Are you serious?
It basically looks like figure skating.
But on skis?
It's pretty actually.
Is it like down a hill?
Did you see the movie?
Down a mountain.
Did you see the movie Blades? Was it Blades of Fury? Blades of Glory.
Blades of Fury.
Yeah, I love the what I was thinking is Balls of Fury, the ping pong movie. Blades. How many of you did not see Blades of Fury?
Blades of Glory.
Blades of Glory. Blades. I combined them. It's good. It's a better movie. You didn't see Blades of Glory?
Even my mom loves that movie.
Yeah, Joey's mom loves that movie.
What?
It's got Will Ferrell in it.
No, I know.
Oh.
I've seen the commercials for it. I have no interest.
It's hilarious. I love the part when they're like practicing the from behind the Iron Curtain. The what's it called, the something Lotus.
Yeah, the Iron Lotus.
The Iron Lotus. And he's just practicing on like dummies over and over again, just keeps decapitating them. And then the guy from the show Coach is just sitting there just sharpening the heck out of the blades. He's looking up and he's just trying to get a real razor edge on him. This dude's just decapitating dummy after dummy. I love that part.
All right, let's go to the live practice.
Yeah.
I'm ready. Just heads all over the place.
Or like how
That shot from North Korea. And they're like, yeah, and the chick's head falls.
Blood everywhere.
or like how tug of war used to be a real Olympic event.
It still is.
Was it really?
Yeah.
They have that one that's across the Mississippi or something. Every year they do it between the two states.
You should be
Well, that's not the Olympics.
No.
What are you, a hillbilly? Well, they do it every year across the Mississippi. It's a little different than the Olympics.
How great would that be?
It still is. Do you know there's actually a sport, underwater hockey?
What? Yeah. I've seen that.
It's a true sport.
That's awesome.
How do you? That's nuts. To the YouTubes. Just whoever
The stick is like almost it's longer than this remote, but maybe two of these remotes, and it has like a little curve on the end of it. And I don't know what the puck is, but you have to stay underwater, but you can't touch the ground or something like that.
What? Wait, you have to stay underwater?
Is it upside down?
They only play it when there's an ice sheet. And basically, you jump in through a hole in the ice. They put a puck that floats on the bottom of the ice, and you have to swim around playing underneath the ice, trying to get into the other person's goal. And if you need to take a breath, you go to the hole in the ice.
Yeah, but I don't. It's possible that's true. That sounds legitimate. But when I first learned about underwater hockey, there was a guy that I went to undergrad with. Well, I was an undergrad, and he was like a professional student. He was probably in his 30s or something like that. But he was the captain of the underwater hockey team at University of Illinois, and they practiced in like a swimming pool. So I don't know. I just know a little bit about it, that what the stick is looking like, and how they kept petitioning every year to get into the Olympics. I'm pretty sure they merged that with maybe real hockey and turned it into quad luge.
Yeah, you turn it on. You can do what Mark was saying and have one game on top of the ice and one below it. That would simultaneously go to the hole and try to get your head cut off. You get Black Lotus. We're tying it all together. The rough around my bottom just like.
Yeah, that's actually part of the. You have somebody on the ice, maybe the goalie of the guys above the ice. The goalie's job is to like warn the other players when somebody's coming up for air, if it's like the opposing team. And then the guys on top need to go do a really like shallow hockey stop, so the blade.
So you could like try to cover the hole with your body so they can't get up enough to breathe.
The game's over either when time runs out or when the opposing underwater team is out of players.
No, wait, they can have it so that like there's still only two teams, but you can go under or over. So you can just go under the ice and come back up. Crazy.
I mean, I'd watch it.
Yeah,
That'd be awesome.
It sounds more interesting than soccer.
I wouldn't play it, but I'd watch it.
Shots fired.
Soccer's so boring. I mean, I have. I don't like baseball either, so I'm with you on that. Baseball's boring. Yeah, no, I have tons and tons and tons of respect for the skill and the athleticism of the soccer players, but that sport is just boring to watch. The games last too long. They just need to have like a sudden death type thing.
There's not enough scoring that.
That's it, yeah.
Sudden death, you don't score within 5 minutes, the ball explodes.
Or just have it be random. Every single time you somebody touches the ball, there's, let's call it a 2% chance of something. You kick it around a ticking time bomb. So again, it's when either somebody scores or the opposing team runs out of players. What's this? Oh, I love that.
Have you seen Gladiator?
I like 300 better.
You can see the second one.
My favorite
I'm
documentary.
going to.
is 300.
It just documents the graphic novel. Did you watch more Game of Thrones?
I have one. Yeah, I finished the 3rd episode.
How about archery? How far are you on that?
About the same, like 5 or 6 episodes in
We
or
should
something.
totally not put those up somewhere where we could all get plays on the Game of Thrones.
What did you think you'd sell? Joey. Wait, you're passive guy.
I have them already converted for iTunes. All right. Shut up. All right, so we need to find out why we're not getting that token. Oh, man. Did you hear that? All right. So we'll go back into our source reader. We've already shown in our node that we are indeed creating nodes for all those guys, so we need to now determine why we're not actually adding those guys in. My guess is it has something to do with our ability to determine if something is an operator or something. Well, no, because we added some of them. Here, let's go into syntax tree, and let's just quickly. I'm going to make this public just for a second, so I can use that variable to do some debugging. So I just made my token variable for my nodes public, so that I can come into syntax tree, and whenever we try to add a op node, system.out.println. Adding op node and token, and then we'll add non-op node in the other one, and let's just see if they're at least all passing through these. Okay, non-op, non-op. Okay, so it's happy with these guys. Shut up! So we're at least trying to add all these to the tree. So ID2. We steal that. Let's get inside an individual node. Oh, you think my display method's broken?
Yeah.
Well, that's a real possibility. If it is broken, I did it on purpose. All right, so this is this.root.display. So that just starts at the top. Go down to node. So we'll print out ourselves. Then we'll print out left. If the left child is equal to null, print out null. Otherwise, we'll tell the left child to print itself. Print out right. If the right child is null, shut up. The right child is equal to null, print out null. Otherwise, tell the right child to display himself. I think that should work. Yeah, I think display is legit. So somehow those guys aren't getting in there. So let's go into node. Adding non-op and dot token. Let's just print out those. Well, that's kind of interesting, actually. This code's never getting called. All right, so that would explain something. So we're never actually calling add non-op node. Let's see why. Syntax tree. Oh, because of this? We didn't finish implementing this? Is that it?
No.
Ask our right node.
This comment actually doesn't do.
Dot
Just a
add non-op. There we go. Well, see, we actually started class with this, and we went and wrote all the required pieces and just never came back and called the method that we wrote. I think this should work now. All right, is that better? Actually, what's kind of interesting about that is, barring the stupidity, this was a working syntax analyzer first run. That's pretty legit. No, because I gave you a warning about this. Remember how I said that when you print out your syntax tree, don't worry about making it look pretty, but I will probably be bothered by... I said that, remember? Well, before we do that, though, let's talk about something that's really, that's fairly important, because we can kind of follow the syntax tree thing here. So, an issue we have, if we come back here, and let me just add another line. A is equal to B divided by C plus 2. Let's just say that. What will our syntax tree look like for this?
Yep. Mike, what did you do?
Question. What should the syntax tree look like? Should there be a second syntax tree for each expression? Or I'm sorry, no, the way I said it's correct right now. For each expression? Because the left and right childs at the leaves are null? Go ahead. For every what? Oh, right. Every node is a tree, but every node isn't necessarily a syntax tree.
Line or whatever in the program would be some little thing to be analyzed.
Some little tree?
Yeah.
Okay. Or at least we could do it that way.
Yeah.
Go ahead, Beaker.
Why are the 3 nulls in a row? Is that where it breaks off into the next line that you had? Yeah, between there.
Well, this was...
That was the end of our last one. Why is there...
Well, sort of. Well, the equal is from the new guy. He's from our new tree.
Right, okay.
So we're like dropping ops in the middle of our previous...
Can you go back to what you had typed in?
Oh,
Yeah,
the code?
Yeah.
A equals B divided by C.
So did A get like dropped or something?
No.
It's actually 60s left.
Yeah.
Yeah, here is 60, and 60's left node that's the A. That's the B. That's C.
Well, since there's no op in between 60 and A, what gets placed there then?
Well, nothing, because it's wrong right now. Because we added a bunch of non-ops in a row.
Well, shouldn't our code have caught that?
Well, it will in the next stage. Yeah, right now we're just trying to throw stuff into a tree so that it's in a format that we can analyze. But this comes back to an issue that we have in programming languages. If we're going to create a tree for each of these, we need to know where the end of one line is and the beginning of the next line. Correct? How do we do that? Most of our programming languages have statements that end, well, C-type programming languages have our statements ending in a semicolon. Right? If we did not end them in a semicolon, what would we have to do? Let's say we didn't choose to end them with a special character. There's some ramifications to that decision. Well, yeah, I guess if it was code that we typed in, I'm talking about the language we're inventing. If we decided not to require you to end it with like a special symbol, like a semicolon, what ramifications come out of that? Go ahead. Okay. 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 We're going down a good path there. What does that ultimately mean then?
Basically, you have like when the new line character itself is picked up.
So that means that when you are finished with a line, you actually press return. Where in a language like Java, you can put your entire program on one line if you want. Okay, so in a language where you don't have delimiters at the end of lines to dictate the end of a statement, if you will, so most languages, the second you put a semicolon at the end of it, it's no longer an expression. Now it's a statement. Okay? It's a self-contained animal, I guess. So if you don't have delimiters at the end of your statements, now when you press return and when you have an opening curly brace and things like that actually start meaning something. Which could then mean that white space is also important. What if you kick 2 lines down? How do you handle comments? So all sorts of things start playing in when you make that one decision. Like, oh, well, why should we make our programmers end the line with something special? Well, because if you don't, the language actually becomes significantly harder to code in. Or maybe mistakes are easier to make. Non-obvious mistakes are easier to make. Those are the nightmare mistakes that are difficult to debug. Okay, so if we decide that in our language we're going to have semicolons at the end of our lines, how would we take that into account in our compiler as we have it written so far?
Stop making a tree.
Well, we actually got to go one step before that. Remember, the tree is built through the token stream. So that token stream is built at the lexical analysis stage. So when we're reading in our source file one character at a time, if we find the character semicolon, what do? You could, or couldn't you just throw it in your token stream? Capture the semicolon as a token and know that statements are divided by that token?
Sure.
Does that make sense? So we come back to our code. We're going to go back into our source reader and go into our Lexical Analyzer. And what does this guy do? It goes through and gets one token at a time. Well, what's a token? So it calls our getToken method. Here's getToken. getToken starts off at something empty, skips until we find something that's not white space, If it's white space, keep reading it in until we finally have a single char. Before we read any more, could we check in here and just see if that single thing is a semicolon? Would that hurt anything? If, well, we can just do it this way. The token dot equals semicolon. If that's a true statement, return the token. Immediately quit this guy. Don't read in any more things. Right? Leave that for the next token to pick up where we left off. So remember, methods immediately end when we have a return statement. So we're just checking to see if we just happen to read in the beginning and end of a single character token, which is the semicolon. Go ahead.
So with that, when we display, will that, when you had to add those nodes, will it only add the nodes in the first selection that you're having, and then after it's been returned to the next line, it'll add more? So we'll have right from that code right there, it'll actually separate them.
Well, no. At this point, we're just splitting up our entire source file into tokens to create a token stream.
Right.
So all we've done at this point is we've decided to treat our semicolon. We look for a semicolon, and we just toss an extra semicolon as a single token into our token stream. That's all we've done at this point. Okay, we haven't taken it any farther than that. So now that we've done that, we go to the bottom here in our source reader. As we're reading through this, let's just do a quick system.out.println read token temp. I still have it public. All right, so this should give us a what? This should show us all the tokens it read in. We're not successfully capturing our semicolons.
It's really pissing me off.
Because there's no space in between?
No space in between it.
Well, didn't we separate it by space originally? And since it's never being actually found because there's no space in between 60 and the...
Oh, no, I get it. So the issue here is that this isn't necessarily the only place that we can have a semicolon. In a language like Java, can we have semicolons any other place other than the end of a statement? Or is semicolons kind of off limits other than to finish statements?
Put them in strings.
Oh, that's
With double quotes, right? Yeah, that's true. It's technically a correct answer to my question. Okay.
Check the.
So down here, before we return something, when we return this, this comes out to our, this comes into Lexical Analyze. We're going to pass that to Lexically Analyze, correct? But before we do that, cur token in here, potentially, by our example right here, could be like a 60 followed by a semicolon, correct? We might need those guys treated as two separate tokens. Go ahead.
When you up there where you just took out the code, check before you add the next.
Why not do it here? By the time we get down here, we know we have a full string. And if there's that semicolon in there, there's a semicolon in there, right? I suppose we could make the argument we could have this issue. Nothing's wrong with that, is it? Nothing's wrong with that. So if we ran this right now, Oh, actually, does it? Oh, it treats the semicolons as identifiers as of right now.
Well, why wouldn't it?
No, that's what it's doing right now. That's not what it should do. We want semicolons to be treated as special. Go ahead.
Do we add it to our language? Like,
So under language reference, we have known operators. Correct? Is a semicolon an operator? Huh? Yes, but unary? Okay.
no, figure it out.
We don't want to treat it like we treat the other operators, do we?
No.
We really need it to be a special case. Okay? So we could, before we even add it to our language reference, let's go in and deal with it directly first. So when I get right here, where am I at? Where am I? Here. Let's print out what we see here. About to Lex cur token. Let's look at what those tokens look like. So we're about to Lex semicolon, standing by itself. Similarly, if we, let me actually give us two different examples. We come in here. So we should have a 2 semicolon as our second one now. So about to Lex I left the space in the one up there, didn't I? Oh, here we go. About the Lex semicolon, and then later on we have 2 semicolon. So we should know whether or not we're dealing with a single semicolon or not, right here. So when I get into my code, where we're doing this about to Lex stuff, I can say if cur token dot equals the string semicolon. If that's a true statement, what do I want to do? I want to say this dot token stream dot add cur token. I'll just go ahead and add that semicolon as a token. Make sense? Else, the only other possibility, other than this is not having a semicolon in it, is we might have a token with a semicolon at the end. Correct? Because we'd never have a semicolon followed by a token. We'd always have a token followed by a semicolon at the end. So, else if cur token dot char at cur token dot length minus 1 is equal to a semicolon. If that's true, then what do we want to do? We want to lexically analyze our cur token dot substring 0 to cur token dot length minus 1. And then this dot token stream dot add semicolon, like that. Else, everything's cool, just do what we used to do. Okay, so right here, if I have a token that contains our semicolon as part of the token, what we're going to do is we're going to first lexically analyze the non-semicolon part of it by taking the substring of that token from bucket 0 all the way up to, but not including, the last legal bucket. That's why I say length -1. And then I'll go ahead and tag on an extra token for my semicolon. That make sense? And then to see this at work, about to process token. And we should see 2 individual semicolons as tokens. There's our first one. Oh, I must have a red token like right underneath it. Yeah, I do. We're doing everything twice. And then my second semicolon right here. Okay? So our code as of right now successfully tokenizes semicolons and treats them as special tokens that we can then next time come back and look at how do we incorporate those into our syntax tree to have multiple syntax trees. That make sense? I'm not doing it yet. Now, I need to now interpret my token stream to know that when I hit a semicolon, that's the end of one syntax tree and the beginning of another one. Capiche? All right, I will see everybody on Monday.
When we